And then okay. Everybody, like, huh? Sam, are you connected? You can see my screen? Okay. All right. Good. So we'll get started. Before I turn it over to Gary, I just have a couple of reminders for you guys. Okay. So I have two unformed groups that are not yet formed groups for Wednesday lab. Make sure before you leave today, whether you're on Zoom or here, make sure that you are in a lab group of 5 people. So I have my list. I can pull it up at the end of class and I can tell you whether or not you are in a group. So if you didn't tell me yet, then you're not in a group. So you have to talk to me before you leave today, because I will send you an email confirming who is in what group, because this decides what chromatography lab you'll be doing next week, whether HPLC or GC. So it's very important we complete this today. There's one other thing that you want to keep in mind. In a group, every week there's a group leader. So you want amongst yourself, you want to pick a leader for each group for next week. Who wants to be the leader? A group leader, meaning you come, you know what you're doing, you divide tasks, and you kind of lead your group. And the group that is the most efficient group and working well together will get +2 in their lab report. So it's kind of like an incentive to have some leadership role and get something out of it. The quiz is on Monday, supposedly, but it's virtual, so it won't happen in the class or during the class period. So what we will do, the quiz is already prepared and is online, but it will open Sunday morning at 9 a.m. and it will close Monday morning at 9 a.m. So you have 24 hours to go in and take that quiz. And it is 30 minutes. So when it starts, you can't pause it, it goes. So it's an honorary system where I expect no books, no texting amongst yourself. And anyway, the questions are going to be randomized. So you will not potentially get the same question in the same order. So please just close your books and turn off your phones and take the quiz within the 30 minutes. If you're done early, that's good, you're done. But we hope within the 30 minutes, you will be able to complete the quiz with no problems. So that's that. With the quiz, there are going to be calculations. So have a piece of paper before you hit start the quiz. Have a piece of paper in front of you, your calculator, so that you can show your calculation on the piece of paper. And one of the questions would ask you to upload or attach your picture. So when you take that picture, you need to upload it to the, yes, Erin? Oh, there's no pages. So it's kind of like you scroll down. So the questions, yeah, I just checked it this morning. The preview is basically, you just scroll from one question to the other. Yeah, so there shouldn't be a problem there. So yeah, so there will be a place where you would attach your calculations. On the quiz itself, you write your final answer, but instead of taking time typing the equations, you can just take a picture of your calculation and upload it. Okay, I will send you this afternoon, details for next week. Of course, like usual, I will hand it over to Gary.
Good. Well, I get the opportunity to talk about gas chromatography. It's something that I've lived for quite a few years at this point. I think I celebrated my 50th work anniversary. So yeah, been in it for a while. And it's always fascinating to me how things advance. Back at the time when we first started this, it's like, wow, how could anybody ever do anything more? And it just continues. Manufacturers, equipment, just keeps on getting better and better and better. It fascinates me. And same thing will happen to you. You'll use equipment properly in this laboratory or other laboratories. Think, wow, it's wonderful, but give a few years, there will be new and innovation. It's really impressive. So, okay, gas chromatography. What do you think the mobile phase is? Anybody want to? Sure. You betcha. Guess. It's kind of a giveaway in a sense. So you've studied or you've learned about general chromatography, chromatographic principles at this point, right? Oh, halfway through it. Okay. And so this is the mobile phase is gas. Stationary phase, we've got quite a few different choices for that. We'll talk a little bit about mobile phase. It's not as important in gas chromatography as it is in liquid chromatography. The mobile phase in liquid chromatography is extremely important. For gas chromatography, it's less so. So we only have a couple choices. We'll talk about them and explain why we do use one over the other. Stationary phases is where we get our separation. At one time, we had over 300 different stationary phases, all quite unique. And today, that's a much smaller number, as you'll see when we get through this. But that's the stationary phase is what's responsible for our success in separating materials. The name, some call it gas liquid chromatography. That's really a misnomer. There's no liquid in this methodology. There's no liquid phase. So that's kind of gone by the wayside. For once upon a time, they're talking about HRGC, high resolution gas chromatography. Why would you have low resolution? Why would you have poor resolution? So, okay, that name kind of went away too. And so now we generally just talk about it as GC, gas chromatography. It's fascinating how many different types of analyses that you will see gas chromatography used for. In class, you're going to look at fatty acid separation on the gas chromatograph. That's a very common usage in our field. But things like cholesterol, we may be interested in gas packaging, some food component. Hey, I can use gas chromatography to look at that gas that's packaged and look at the packaging material. Is it leaking? Do we still have the same composition inside that package over storage? So gases. We may be looking at solvents used in some applications, extracting foods, extracting fat. Well, is that solvent pure? Does it contain materials we really don't want in our food supply? Alcohol, gosh, maybe we're in the distilled industry, okay, distilled beverage industry. We are interested, is there ethanol and how much ethanol? But you can kind of go through this list and it's just a partial list of actually where it's used. Sometimes it's used maybe where it's not the easiest or the best, but it's amazing the wide variety of applications that you will find with it. You'll notice in here, amino acids are listed. And I think probably LC does a little better at that than GC. Let's see what else. Well, that's, I guess on this list, that's the only one that I'd say maybe doesn't belong there. You might say sugars. Sugars aren't volatile. We need to get our sample into the gas mobile phase. Do sugars go into the gas phase? Not really, but we make them volatile. We do a derivative of the sugar and now it's volatile. We can separate them. So again, just a large host of applications, many more than show here. From a historical standpoint, chromatography certainly started some time ago, been around a long time. 1906, plant pigments, 1850. When you get to gas chromatography, the important date's 1941. That's the first theoretical discussion of can we use a gas as a mobile phase? Took 11 years from that kind of initial thought to actually making a piece of equipment. So the first real gas chromatograph was made in 1952. Clumsy, awkward, whatever, but it was a machine that had a mobile phase and could do separations. Our biggest problem in 1952 is we didn't have any good way of detecting things that are eluted, things that are separated in the end. 1954, they developed the first detector so we could have this separation occur, things eluting off in the gas phase, and they could be measured easily. And so today, actually, it is a mature technique. I could probably say 20 years ago, it was a mature technique. We've met all of the theoretical maxima in terms of possibility. So it isn't going to get any better than it was actually 20 years ago in terms of separating ability. That doesn't keep equipment manufacturers from offering something new, something different, something simpler. So you keep on buying. It's kind of like the market today, right? Let's create a need so you can buy our equipment. So it's just getting a little fancier, gotten a little more convenient, but it's absolutely no better in terms of separating abilities than it was 20 years ago. So what are the processes? If our material isn't a gas, and most of the time it isn't, it's a liquid or a solid, we have to, one way or another, vaporize that sample, put it into gas so it can follow the carrier gas through the system. As this material goes through that column, of course, there's an interaction with the coating on the inside. Right now, we have a very, very small glass column that you'll see when you go to laboratory. Very, very fine glass tubing, and there's a coating inside that tubing. And what we look at is how our analytes, do they like that glass coating material inside? Do they want to stay in there so they kind of hang up a little bit? Do some like it less and they move faster with the gas? So really, we look at interaction between the material. Does it want to be the gas moving along, or does it get retarded by interacting with that liquid? Not liquid coating, let's just say with that coating on the inside. Separation hopefully occurs. It's a marvelous technique, marvelously efficient in terms of separation, but we don't always get separation, and we'll deal a little bit more with that later on when we get a little more advanced into this topic. But a very powerful tool. And then we have to somehow detect what's coming out. And there's where some real advances that have occurred. At one time, the first gas chromatographs, they were collecting the vapors as they came out of this column, and the tube condensed them, took them over and titrated them. Well, we got a long ways from collecting things in the tube and titrating them. And so we've got a lot of options. I'll spend a little bit of time talking with them. And again, how these new detectors advances have advanced our ability to separate and measure things as well. So we have seen some good things happen in these lines. These are the parts of a gas chromatograph, kind of the major parts. How's that? There's a lot more small ones. So what do we need? We need a gas, right? So you're going to find a cylinder of compressed gas. We'll talk about that. Typically it's helium, doesn't have to be, but helium. It's very inert. We don't want a real active gas. We want a carrier that's inert. Okay, so there's helium, nice inert sample, or a carrier gas. We have to have some way to inject our sample to put our whatever it is, an extract, a gas, whatever you want to analyze. We got to inject that into this gas stream. So it gets into that column and starts our separation. And so in that case, see if we get, we do get a mouse moving, yes. So can you see that? Uh-oh. Oh, back over here?
So you want to move it to the left, then it shows up here.
Right, left.
Your left, I think. I see.
I got a mouse here. That doesn't.
So see, this mouse here, if you go to the left, then it shows up here for you.
Okay, that's awkward. I'll probably point up there.
Oh.
Okay. Okay, so we've got our column, and that column can be something like a meter. It can be 100 meters, if you can envision 100 meters in length. So, okay, we've got a column in there. It's going to come out that column and it's going to go into a detector. And so again, we'll talk about different types of detectors. And ultimately, we're going to get a printout, something that shows up on your computer screen. And it does more than show up there because the system is always measuring that peak. How big is that peak? What's the area under that peak? The bigger the peak, obviously, the more material. So it does a nice job of calculating area under the peak. So we get a nice drawing, what's our separation, and we get a basis for quantitation. So now we've added a few more parts to that, but it's exactly the same system in a sense. We've got our carrier gas, but normally you'll find two other gases always sitting next to that instrument. And one is hydrogen and one is air. And these are what feed the detector. So this happens to have what we call a flame ionization detector. Hydrogen burns. But what does it need? It needs air. So we got hydrogen and air. So as things come off, our analytes of interest come off that column, they get burned in a flame. And we measure the ions in that flame that's burning. Again, I'll show you that in a little more detail. So if that sounds a little weird, you'll get a picture of it in a better sense. So again, there's our flow controllers. We have to control pressure. We've got to control how fast the gases flow, how fast they go through that column and so on. It shows just a little bit more in terms of the equipment itself. So kind of looking at that very beginning, our gases, they have to be high purity. We can detect somewhere around, 10 to the minus 10th, maybe, grams of material, 10 to the minus 12th grams of material. That's our detection limit. So if there's something in that gas, in that system anywhere that's in that ballpark, I'm going to get another peak. I'm going to get another compound that's an artifact. So I want those gases to be really pure. So helium or hydrogen, like I say, is our mobile phase. They have to be ultra high purity. The detector gases, the flame detector, yep, we need a flame, we need hydrogen. But some of the other detectors that we'll go through, and I just have abbreviations, MS for mass spectrometry, TCD, thermal conductivity detector, I'll talk about them. Some detectors require gases, some don't. And we'll see a little bit about that as we go along as well. We have to have really good control of our flows, our mobile phase flow rate. We have to have absolute control. And so they have really sophisticated, high quality flow controllers. They're typically stainless steel, and they are ultimate in terms of purity, quality, no contaminants. Sometimes people say, I can get this down at the welding shop. No, you can't. I can get the hardware store. No, you can't. It's same like as the gases. You go ultra high purity. You can't get general gases or general, for that matter, equipment in this system. So they are precision and they are well done. So here's kind of, we'll go through this inlet, we'll go through this gas chromatographic system. Over here we have on your right, we have the injection port. So we need to get our sample into a pressurized stream of gas, our mobile phase. That mobile phase is under pressure. It's moving the gas along through the column. And so we got to find one way or another to inject into a pressurized system. And so it's done with this particular injection port. Up at the top, you'll see an opening. There's a small opening up on the top that goes down. And that has a rubber septum. I shouldn't say rubber, that's a high purity silicone septum. How's that? A nice little disc that sits at the very top and seals the gas off so it doesn't go back out the very top of the instrument. And what you're going to do is you're going to take a very small syringe, like a 10 microliter syringe. You're going to go ahead and pierce it down through that septum. and inject into that injection port. So you'll inject maybe about 1/3 of the way down. And that's where then you tap the top of your syringe, that injects your, whatever sample you had or sprays into there, you pull it back out, and the system goes on its merry, merry way. As you'll see different parts of this, that is hot. Typically, our injection ports run around 250 degrees centigrade. And so, you put that in Fahrenheit, you got a pretty warm oven. nice and hot system. When you go ahead and tap the syringe and it sprays your sample into there, it becomes volatile. And so that turns it into a gas. It goes down our injection port liner and it comes out the bottom where that's connected to your column, your analytical column. We have different types, different configurations of these systems. It's interesting that normally we will do some kind of a split. We'll put our sample in there, it'll become vaporized, but I don't necessarily want to put everything I just vaporized into my tiny column. I want to have a big enough sample I can measure it. So, okay, I got 1 microliter, 5, 10 microliters. I can measure that accurately, but that's too much then to get into the column. So it seems kind of weird. You inject too much because you can measure it, and then you split it. So only one portion of that goes in. Maybe 1/20th, 1/50th of what you injected actually gets into your analytical column. The rest gets vented out into the room, basically. So say only a portion of the material gets injected in the split. So this is our split injection. So the different types of injection ports. Some systems are set up so everything that you put in goes on that column. And I'll try to give you an example of that. In some cases, we have what we call an on column, and I'll show you configuration for this. Some materials are heat sensitive. If I inject them into 250 degrees centigrade, they go all poof and turn into something I didn't want. And so, okay, you've got to have an option whereby that's cold. And that's just a little different way to do it. We'll go through that too. Finally, we have some injection ports that are designed to be cool, make your injection, and they warm up about 50 degrees per second. So they come up very quickly to vaporize your sample. So many different configurations for how you get your sample into the system. Some actually are set up to be high volume. You can inject a milliliter. That's absolutely amazing. Normally we look at 1 microliter to 10 microliters. So again, different configurations, different ways to make injections. So this is the split injection. And so we've got, as an example, we have 54 mils of gas coming in. That's our carrier gas. Our nice inert helium, hydrogen, whatever. So we've got 54 mils per minute coming into the system. That kind of cap at the top is where we put our syringe in, and we have to pierce this septum. And so that septum at 250 degrees centigrade sometimes gives off impurities too. So right across we've got 54 mils coming in, but only 3 mils actually go out a vent. And that's kind of a pathway so that any garbage, I call it garbage, that's coming off of that hot septum doesn't get into our system because any vapors that come off there get swept out there. We make our injection in two. The injection port over here, and so we put our syringe in, we make our injection. And so we got 54 mils coming in, 3 mils go that way. That means 51 are coming down our glass tube, the center of that injection port. So 51 mils per minute are going here. That column is tiny. I can get about 1 mil per minute, maybe 2 mils per minute coming through this little column that goes to the detector. So of that 51, maybe 1 goes into our column and 50 parts go out another exit. So that's our splitter. We got a 50-to-1 split. Whatever I injected, 1/50 of it goes on the column. I can change that a little bit. I could decrease my flow. Maybe I could go 1 to 20. So I have some flexibility here. But basically, that gives you a split that's ideal for the column, its capabilities, its separating powers. If we do a splitless, we do it a little bit different. In that case, we could have 54 mils per minute coming in. Yep, we can have this septum purge, keeping things clean up there. But the way it works is you put your syringe in, you make your injection, and it shuts off this vent, the second one on the bottom here, PC valve right there. It shuts that off, and then everything, any gas, has to go through the column, at least for some time. And so you've got all of your sample vapor in there, and for maybe 1 minute, 2 minutes, it keeps on dumping into the column, and then the valve changes and it cleans out. So you can put on, instead of a very, very short sample, you can put on a big sample of what you vaporized in the system. So we've got samples that are really low in concentration. You really want to get the best sensitivity you can. You do something like this. If you're not limited in sample, you use the first choice. Cleanest, quickest, nicest separation on the system. This one you pay a little bit in terms of separation. Our on column is a different type of injection port. This is a rather interesting one. There's an inlet valve up there where it's labeled. You can actually take a syringe. Now, if you look at a 10 microliter syringe, it has a needle of something like that long. Well, here, my syringes can have a needle about that long. And so I'm going to pull up my sample into the syringe. I'm going to actually push the septum right down through that inlet valve. That inlet valve is a little flexible. It opens up as I'm pushing this needle down through. And so your needle can get all the way down into the column itself. That column may be 40 degrees centigrade. So by the time you get your needle down there, it's cool. It's only 40 degrees centigrade. So if you're working with compounds, maybe that are not stable to heat, you'd use this simple system here. There's no heat on the system at all. So you can just go ahead and put a long needle in and make your injection into the bottom of that column. So different injection ports, splitless, on column are the three major ways to get your sample into this gas stream. So our next place is, okay, we get our sample now in our column. So what kind of a column do we have? Well, back in my days of starting chromatography, we had a column maybe a little smaller than my finger in terms of diameter, but not much smaller than my finger in diameter. And they were typically 6 feet, 8 feet in length. So you'd have this tubing, really what I call today a big tubing wrapped up. And there would be a packing inside. It'd be a granular material, a little bigger than any kind of food powder you see around. And that material is inert, but it has a coating on it. So we've got lots of powder that's coated. And it's coated with materials that will interact with your flavors, with your compounds, whatever you're separating. If your analytes like that coating, they're going to hang around that coating. Oh, okay, I'll release. I'll go to the next one. And they keep on traveling through the system. And so we used to use packed columns. That's all we had. Today, they're hard to find. I think I still have a couple upstairs just to kind of remind me. How's that? What we have today is, of course, capillary tubings. And so they're typically open tube capillary. There's no packing inside. Your stationary phase is just a coating on the inside of that tube. So as your analyte's going through that glass column, that glass tube, it likes the coating and kind of hangs out in the wall a little bit. Now, okay, I'm going. We get separation. If they like to be in that coating, they hang around longer. If they don't like to be in that coating, they whiz through. So that's basically what gives you the separation. Do your analytes like that coating, want to be soluble in it, want to hang out in it, or do they not and want to move through? So it's an interaction. Most of our columns, as I say, they're called open tubular columns. That's most common. There is a PLOT column. It's porous layer open tubular. And in that case, there is a rough packing material. It's a really, really fine material that's deposited inside this very, very small glass tubing. They're very uncommon. We find them very, very special applications. So we might put different materials that we couldn't put in a liquid form or we couldn't bind to the inside of a column. And so porous layer open tubular columns are used. You won't find them often. You'll find most commonly this glass tube with a coating on the inside of that glass tube. The columns today are fused silica. They're very fascinating to me. I should always bring an example, but you'll get to see an example in laboratory. So I don't know how many of you ever tried to take a glass tube and tie it in a knot. Has anyone ever given that a try? No? How come? You assume it's not going to work too well, right? And that's the case, obviously. But this tubing is so pure, it's so thin-walled, you can take your length, 6 feet, 6 inches, you can tie it in a knot. Glass tied in a knot. Just because the diameters are so small and they're so strong and so pure. So they're really handy from that standpoint. Back when we had really glass tubings that were 1/4 inch, they weren't bendable. You found out very quickly if you tightened them wrong that they're also fragile. So we've seen a really nice transition to this ultra pure glass. There's a melting point of 2,600 degrees centigrade. Now, regular glass melts well before that. What are diameters on these things? The diameter of our columns range anywhere from 0.1 millimeter to 0.53 millimeters. We're talking tiny. The length can range anywhere from 1 meter from where you inject it to where the detector is, or it can have 60 meters of a column in length. So range from small, short to, again, 0.53 isn't really big either, but okay, 0.53 up to 60 meters. And then, like I say, we put a coating inside of that tubing. And that coating will range anywhere from 0.1 microns up to 5 microns. So again, we got some variables: diameter, length, coating, thickness of coating, and so on. But I think I said it once, at one time we had over 300 different coatings for packed columns. Well, this is our list today. 1, 2, 3, 4, 5, 6, 7, 8, 9 or something like that. It depends on how I count it. We have 9 different coatings instead of over 300 different coatings. Our old technology, we didn't coat well. It was a problem. We really had to depend upon that coating to do a job for us. Today, our efficiency is so good, we don't have to have the same selectivity of our coating. We can get by with 10 different coatings, and that's all we need. And that's really an advantage in terms of inventory, keeping things on hand. There's a question, one of the first questions you come up with if you're doing this type of job and somebody brings you a sample is, okay, I've got 10 different choices for a coating. Which one do I use? That's a question, and a very reasonable one. And so the idea, how do you make a selection? How do you choose that coating? Is, first of all, you go to published information. You'll be amazed at all the things that have been found, all the things that have been tried. And you just do a Google search. How's that? And you say, I want to separate, oh gosh, to pick something, lemon juice components. Okay, I'll pick a flavor. Flavor's my bag. Okay, so how do we want to separate lemon? There's about 180, maybe 200 different chemicals in lemon flavor. I want to separate them. And you'd find an article come up, you would look at the methodology, you'd see what they did, and that's probably where you'd start. Somebody's done it. Like I say, there aren't many things in the world that haven't been done someplace, sometime by someone. And so that's always the simplest way today to go about this. There's also a publication of how different compounds separate on columns. So there's a compilation. Somebody's gone through the literature and they say, well, this compound is easily separated on this particular coding, particular column. And so you can simply look at that well as well. Retention indices, what's the elution time? How does it separate in a column? So that's a little different. Published information, that's a method. Somebody has a method, they tried it out. The retention is, I've got a pure compound, how does it chromatograph? How does it run? How does it behave on different columns? Journal articles, that can be, of course, the published information. And if you're doing this in a company, you know, chances are someone in the company before you has done this too. And that's really where internal libraries, internal access, has this ever been done in-house in your company? And so you also look for internal work. If you can't find anything in-house, you can't find anything in the literature, you can't find any compilation, you simply look at intuition. Do you have any feeling what type of compound it is that you want to do a separation of? And the idea is, if you have some knowledge of what you want to separate, you have some idea of structure, and you look for a similar structure in your phases, in your column codings. Because kind of like attracts like in that sense. And so you can kind of do some intuition. If you have absolutely no idea, and that does happen. I had a person bring in a piece of drywall from their house one day and said, Professor Anexis, this really stinks. Can you help me? I don't have much of an idea why a person's piece of drywall in their house would stink. How's that? And so, you know, you don't have much to go on. So if you're in a situation where you can find anything, you really start off what we would call a non-polar column, and you'll see them in a moment. That non-polar column is exceedingly durable. I can put them in the gas chromatograph. I can run them up to 200 degrees, 300 degrees centigrade. I can take them up to 400 degrees centigrade. And they are still happy, smiling. You know, we take some other types of columns, polar columns, put them up to 400 degrees and they're evaporated. So I pick a very durable column and make an injection on it. Do I get separation? If I don't get separation, if I don't find anything, then I go to polar, but okay, they're much more fragile. So simply start off with a non-polar column and see what you get. You know, I said that this is an exceptionally good method for separation, very powerful method for separation. One of the most, not number one, but it's probably number two in terms of chromatographic techniques. And okay, are you going to protest? You want Elsie in there?
Number one.
What's that? Oh, no, I've been demoted.
Okay.
It's now number two. And so, but it is, being number two isn't bad, okay? We tease each other. Your instructor likes liquid chromatography, and I tend to like gas chromatography, so we do trash each other a bit for fun. So anyway, why is this a good technique? Well, it takes advantage of different types of chemistry, different types of chromatography. We look at our possibilities. We can have an absorption column, and I know we get some of the same in LC, but we've got some other things going for us. But absorption chromatography, you've got a granular material perhaps, and your material will elute through what you have an interest, your gas phase moving through, and you kind of look at an interaction on the surface of that material. So that are your analytes absorbing onto this material and then being given up, absorbing, given up, so we get separation. And so we can take advantage of adsorption chromatography, molecular exclusion, and again, molecular exclusion. In that case, your stationary phase actually is porous. And you make an injection, and whether or not the pores are big enough to let your analytes in or not, you get separation. Have you gone through the? Okay, so this will be continued. Okay, so again, you take advantage of pore size pathways for separation. And again, you can do that in this technology. Partitioning, that's most common. I tell you, we've got a coating inside this glass. Our analyte's going to dissolve in that coating and be released, adsorb and release, so they actually permeate, dissolve, and come out. That's partition chromatography. Then on top of that, where we benefit too, is we can also separate or reduce separate based on volatility or vapor pressure. So when I do gas chromatography, I can have my analysis at 40 degrees centigrade, and I can run it up to 250 degrees centigrade. And so if it's at 40 degrees centigrade, things that aren't very volatile, they're not going to go anywhere. They just sit at the front of the column. But then they start programming. Oh, I like that. I'll go to the gas stream. So I use temperature volatility for separation as well. So we got several different things going for us that make this a very, very powerful technique. As I said, our stationary phases range in polarity. They're ranked on being polar or non-polar. Our most polar column is called carbowax, the type of material. It's really not a wax, it's an ester. Then we have our non-polar, which are silicone-based materials. And every company has their own trade name. It's kind of like many things in life, right? Same material, but I call it this, somebody else calls it that. And so we'll see that in a little bit. So polar to non-polar, we got that range of the 10. They were actually listed in order of polarity in that table that we had. So sure, different columns. And again, we'll deal more with that later on. As I said, we take advantage of heating, temperature, volatility, drive our materials into a gas phase so they move along their merry way. And so we carry out our separation in an oven. That oven, like I say, will run, actually they'll run anywhere from minus 60 degrees centigrade to about 400 degrees centigrade. So that again does a great deal towards helping us in our separation. So detectors, what are detectors for? It's probably a giveaway, isn't it? They're to detect things. So we get a separation. Things hopefully are eluting kind of one at a time when this gas stream is moving along or mobile phase is. We have to have some way to detect what's eluding from our column. And I was looking at this and thinking, why on earth didn't I update this? Those are horrible peaks. They may be okay for liquid chromatography, but well, I'm sorry. I couldn't help myself. Cheap shot. They're much sharper than that, obviously. And for illustration purposes, the person that did this kind of drew them like that and that. If we ever saw anything like that, we would probably resign. We would throw away the column. Yes, very, very quickly. And so the idea of a detector is to turn, an analyte in concentration of an analyte into some electrical response so that we can draw a curve and then we can measure the area under that curve. The greater the area under that curve, the greater the amount of material. So there's that relationship. But again, we would never be happy with those kinds of peaks. It's hard to say when they start exactly. Okay, maybe you can figure out where the top is, but you'd like to see them, about that wide. You can't see that. How about 2 millimeters wide instead of something like that? A nice, sharp, more accurate measurement. So anyway. Detectors, so okay. We basically are using a detector to get an electrical signal that we can then analyze. And so there's many different detectors as well. They vary in sensitivity and they vary in selectivity. So they may be responding only to some types of analytes and completely ignore other analytes. In some cases, they're immensely sensitive. In other cases, they can be less sensitive. And so we will talk about the most common types of detectors. What time is class in? 3 minutes. Okay, I've only got 30 slides. I can do it. So you guys should have panicked, not her. Okay, so this was the first detector that was designed. And it's still around today. It's called a thermal conductivity detector. And so what we've got is we've got two detectors, one on the left here, one on the right. And so there are two detectors. They have a gas flow through them as a reference. So your mobile phase goes through as a reference. And there's an electrical filament in there. And as that gas goes past the electrical filament, it cools that filament and changes its electrical resistance. So that's our standard, that's our reference. The other one on the right is attached to that column, that analytical column. And as the gas flows through there, it also does cooling, but it's not only the gas, it's another component. And it cools that filament more or less. And so what it does is it changes electrical resistance, the one on the right versus the one on the left. And so you're measuring a difference between the two. It's a nice detector in some ways. It'll detect anything, including water. The only thing you can't detect is it can't detect the mobile phase, because that's what's going through the reference. That's our standard. And so if you've got helium as your mobile phase, it'll detect any substance that's in the gas phase except helium. It's called a universal detector, sensitive to 10 to the minus 7th grams per second. So if we get at least 10 to the minus 7th grams of an analyte coming through, it'll detect it. That's really poor, but it has an advantage. Like I say, it's universal. So it's a universal detector. 10 to the minus 7 grams, you might say that's not too bad. It's not very good in comparison to the competing detectors. Also, linearity is important. If a peak is bigger, is it proportionally more material there? Is it linear response between quantity and peak height or peak area? And again, it's only 10 to the 4th, linear over 10,000 times. So if it's more than 10,000 times difference in concentration, it's not linear. And you might say that's pretty good, but it isn't. So, okay, great detector because it detects anything not as sensitive we'd like, not as linear as we would like. I use up my 3 minutes? I do? Okay.
It says, what is the purpose of low temperature GC? Really volatile gas samples?
I mean, why would we be running at minus 60 degrees centigrade oven? It would be in some cases gases, but in most cases it suits a different purpose. What we might do is we might inject a gas sample from a package into the system. And I might have a syringe, 1-2 milliliter syringe, and I'm going to push this in slowly, slowly, slowly. If I can freeze my sample, I'm putting my sample in, if I can freeze it in one spot and can, condense, 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 and then warm up that oven quickly, it gives me concentration without spreading throughout the column. I don't know if that made sense or not, but basically you bring the temperature down so you can condense your sample so you can start over with the separation. Okay. Otherwise, that's kind of low temperature for doing separations, yes. It's more to condense sample. Good.
Thank you, Gary. Gary will continue on Wednesday, and I will continue chromatography January on Monday. If you have a group already, you can leave. If you don't have a group, especially the Wednesday lab group, please stay, whether you're online or in the room. If you have a group, have a great weekend, and I'll see everybody next week. Thanks, Gary.
You know what did happen is that Terry
And
canceled.
there's a question in the chat.
Cancel the group?
Yes.
Oh, you can
So
continue
I
with
could
that?
have, I could have.
Okay.
And I will. If it's
Oh,
up to
okay.
you.
I will touch base with you. I think it makes sense to continue on Monday. Yeah.
Otherwise, I might forget it all.
Okay. All right.
May I keep this?
Yes, you can keep it. It's yours.
Okay.
All right. Yes.
There's a question on the chat about the quiz.
Question on the chat about. Oh, okay. So what would you want me to explain about the quiz? What was the question exactly?
Like the format of the quiz, or like how does it look like? The format of the quiz.
The format of the quiz. Okay, if you go to Canvas, Moodles, the top part of the page says sample quizzes from last year. So you go there and you'll see sample quizzes. It will be very similar to these quizzes, but definitely different questions.
Okay, awesome. Thank you.
All right. So I'm just going to open my Excel sheet to see who needs to be in a group. And let's see here, lab groups. Okay, I'm going to share my screen. And you guys can tell me which group you want to be part of if you don't have a group yet. All right, so Monday we have that set. And then we have a group on Wednesday that would need one more person to
I
go
can be
in.
a part of that group.
Huh? What's up?
I can be a part of that group if they need one more person.
Okay, Katie. Then let's put Katie here with your last name.
Ashbrook?
Huh?
Ashbrook? A-S.
Oh yeah, I see your name on your screen. Ash Brooke. Thank you so much, Katie. Okay, now we have group F. We need 3 more students in group F. We have Steve and Chris in group F, but we don't have, we need 3 more. So who doesn't have a group yet?
I don't for Wednesday.
Emily, do you want to be on, well, obviously you have to be on this group because we're done. Branko, okay, and you're on Monday? Yeah. Oh, Monday, I think we have, what's your, huh? UN, okay, yeah, UN, you're in group B with, I will send who your group mates are. Okay, yeah. Okay, so now I need, who's missing? There's 2 more people that doesn't have a group. I will just assign the last 2 people to group F then. Okay, with that, I'll send an email with the exact group letter and who's in your group for you to know and be prepared for Monday. All right, thank you, everybody. Bye.
So many things.
Hmm?
We're trying to do so many